Hi again. The next thing that we want to go through in this review is something to do with forces and stresses. In the previous video, we discussed things related to velocity and kinematics. But as you know, kinematics doesn't tell us anything about forces involved in the problem that we are investigating. To really think about forces in a general problem, we always have to be careful about the fact that force is a vector. So it has indeed in 3D space 3 components. But at the same time, when we talk about fluid elements, we know that fluid elements can also move their position, and based on different positions that they take, the area of the fluid element can have different orientations. We all have felt when we are moving in a car, as we bring our hand out of the window, we feel a different force if we keep our hand like this or if we keep it like this. The fact that orientation of a fluid element and the force that the fluid element feels are coupled in some way together tells us that we need to be taking account of not only the orientation of the force, but also the orientation of the surface area element that we are looking at. Take a volume of fluid like this. We can draw many small elements of area on the surface of this volume. Each element of area that we draw has a normal vector n that is orthogonal to the fluid element on the area. And the area of that element, dA, as a vector can be defined as n, this unit vector, multiplied to the magnitude of the area, which is dA. So you can clearly see that as I move around this object, I have different n vectors depending on where and what location I'm looking at the object. If you have a force at the same time acting on this fluid element, it may have an orientation of itself, like for example the F force that I have drawn here. To have a consistent way of keeping these forces and areas all taken into record as we move from one problem to another, or one fluid element in the problem to another fluid element in a problem, we defined a very useful concept known as a stress tensor. A stress is nothing other than this force divided by area. But since each of them has 3 vectors, I'm dividing a vector on another vector. And if you remind yourself of linear algebra and other things that you have seen before, when we divide a 3-element matrix over another 3-element matrix, so it's 3, 1, 3, 1, what we will get out of it is a 3 by 3 matrix. So really a stress is a second-rank tensor. It's not really a matrix, it's a second-rank tensor as we discussed. And it's defined as the stress being a tensor. Each element of it is the dyadic product of EI and EJ, which means that tau ij that I have here is the stress element that is acting in the jth direction, that is working or is imposed on a fluid element that has a normal parallel to the ith direction. So that's the idea. Tau 1, 2, for example, is towards the second direction, but is acting on a fluid element that has a normal that goes towards the first direction. So 1 can be x, 2 can be y, for example, in Cartesian coordinate system. Or in other coordinate systems, this can be r and theta, for example, if you choose a cylindrical coordinate system. But the basic idea is we really write down things for a known standard cube, and once we know things such as tau 1, 1, if this is, for example, our one direction, or tau 1, 2, if this is our second direction, and if this is our third direction, something like tau 1, 3. Once we write down these components using this concept, then we can actually find the resulting net force acting on the fluid elements if it has any arbitrary orientation in space. And how we do that is based on this definition, this simple definition that we have provided here. It's a very simple idea, and we can write it together. Before doing that, let's remind ourselves some of the important properties of tensors that we covered in the class. First important property that you guys probably remember is the fact that the stress tensor is symmetric. And that is valid whenever we have conservative body forces. If we have any non-conservative body force, for example, in electromagnetic fields or magnetohydrodynamic cases, we may have such a case, this statement may not be valid anymore. But in the cases that we study in the class, you can always assume that the stress tensor is symmetric. If this symmetry is not there, you gain a huge, almost infinitely large value or diverging value of spinning for a single fluid element when you write down the balance of torques and moments acting on a fluid element. And that's the result that you have seen in the lecture. The second conclusion that we got from analysis of a stress tensor was the idea that for cases of a static equilibrium, and a static equilibrium means there is no relative motion of fluid elements, we have this condition that the stress tensor of the equilibrium is simply 0 everywhere other than the diagonal components, and the diagonal component is the same for 1, 1, 1, 2, 2, and 3, 3, and is defined as P, which is pressure, and the pressure is by definition a positive scalar. And by convention, since pressure is pushing things inward, we have this negative sign. You can easily show that if you have any condition other than this, if you have any non-zero shear stress, by definition a fluid element or any liquid will not sustain any shear stresses. It has to move, and when you impose shear stresses, it will move and it will not be in a static equilibrium. If somebody may say, okay, I can have 0 shear stresses everywhere, but diagonal components can be different. Here I can have 1 P, here I can have another P, for example, 2 times P. Again, you can show that, okay, if you choose that, by certain rotation of your coordinate system, you can find a stress tensor in a new orientation that will have non-zero shear stresses. So there will be some orientation at which fluid elements would feel the shear stress and will start moving. The only condition that will give you real static equilibrium in fluid mechanics problems is when the equilibrium shear stress tensor has only diagonal components that they are all equal to each other, and that's what we call pressure. Now, if you think about this simple idea, we can ask ourselves, okay, how can we really use the stress tensor to talk about the net force that the volume of fluid feels? And that was the idea that was covered in the class, and that's the third most important concept coming from the stress tensor. I'm going to write it down here. So number 3 is the idea that the traction, which is F, and it's a force acting on the fluid element as I've drawn there, is equal to the normal vector of the fluid element N dotted to the shear stress tensor, which is tau. And once we have this relationship, we can actually go one step even further. This is the traction force that is acting on this small element. If I take an entire surface integral of all these small forces, I will find the net force that is acting on that blob or volume of fluid. Let's do that together. So we can calculate, so the net force will be equal to integral over the area of N dotted to tau dA. And here's the point that we use Gauss theorem, and based on Gauss theorem, this integral simply is equal to the volumetric integral of divergence of the stress tensor integrated over the entire volume of the fluid elements within the surface area that we are integrating. So we converted an area integral to a volume integral using Gauss or divergence theorem. If you again go back to your notes, you will see that actually this was a very helpful concept, because it told us that once we have a certain element of fluid element with a certain stress field and a stress tensor around it, how can we write down the equation of motion for that fluid element? And if you remind yourself, that was how we derived equation of motion for fluid elements, which in absence of viscous stresses, we call that Euler equation. And let's do that together here. If you take a fluid element like this small cube, by writing the equation of motion for it, you can easily notice that there is probably some acceleration that this fluid element has, which I show as vector A, which by definition is equal to dv divided by dt. And this acceleration should be times mass per unit volume, which is rho A, should be sum of the forces acting on the fluid element per unit volume. And we discussed about two sources of forces. One is the body force that can always act from the center of mass of this fluid element parallel to the gravitational vector, and its value per unit volume is rho g. And the other source of forces that is acting on this fluid element comes from the surface forces, that comes from the stress tensor like this. And in static equilibrium, or cases where viscous stresses, which are the off-diagonal elements, are not important, then it will be just the pressure that is acting. And that extra pressure would be captured by the per unit volume by grad P with the negative sign that we have here. In short, if we write down the balance of forces for this fluid element, we get that mass times acceleration per unit volume, which is rho dv over dt, is equal to the sum of all the forces acting. And we have again surface forces, which are captured as gradient of pressure field. And indeed, as always, we have the body weight, or the weight of fluid elements per unit volume, which is rho g term. This is the concept of Euler equation, and is valid for inviscid flows or fluids. So now we have seen the usefulness of the idea of a stress tensor, because it can help us to rationally describe the forces that are acting on a fluid element. And we use that in finding out that the only thing that we need to worry about if the flow is in viscid and viscous stresses are not important is the gradient of the pressure field. That's the only element from the stress tensor that will give fluid elements a net force as a surface force. On a differential fluid element, we got this result, which we called Euler equation. And it's a simple balance of forces acting on the fluid element, giving rise to the net acceleration of that fluid element. Now, if you remember, we went one step further than this. We took this differential form, and then we looked at the overall, for example, force that a body of fluid or a volume of fluid such as this will feel due to the pressure field around it. And we discussed what would happen to that when we have cases such as hydrostatics or rigid body motion or rigid body acceleration. In the next video, we'll start talking about that, and we'll do a quick review of those concepts.